next speaker is James Schwartz from Wichita State University. He's in the faculty of the philosophy department, talking about near-Earth resources, short-term limitations, and interstellar consequences. So please join me in welcoming him.
Thank you, Nick. So I guess I want to start with a question. How many folks were here at the 2016 meeting for John Lewis's keynote? Anybody around for that? A couple people. So this talk is kind of a response to John's keynote in many ways. So I remember John talking about how with the resources of asteroids alone, the solar system can support on the order of, I don't know, like quadrillions of human beings. And I want to sort of push against the mindset that might engender among those of us interested in exploiting space resources for all kinds of purposes. And I've also got a prediction I want to make, which is that there will never be crewed interstellar missions unless we, as sort of humans living in space, get at least to the main belt. So if we're stuck in near-Earth space, we are not sending human persons to interstellar missions. So the success of those missions depends on being able to extend quite a bit into the solar system. And of course, their cost as an overall percentage of human revenues is much smaller than they would be if we're trying to do that right now. My publisher would be remiss if I didn't mention I've got a book coming out early next year, The Value of Science in Space Exploration with Oxford. And there I'm sort of laying out, if you think space science is something that's important, can we say something substantive about why that is and how that ought to impact policy? And the talk I'm giving today is kind of an excerpt of one of the chapters of that book devoted to space resource exploitation and policy. But anyway, so I want to sort of focus on near-Earth resources. And of course, these are often identified as a starting point for getting an expanding and permanent human presence in space. Let's, use the stuff close by first. All right, and to sort of quote some John Lewis stuff here, so from the near-Earth asteroid population at least, John Lewis tells us we can expect on the order of 75 quadrillion kilograms of silicates, around 10 quadrillion kilograms of ferrous metals, and 5 quadrillion kilograms of water. Now that's approximately 1 Lake Michigan if you're keeping track. All right. Just a little more about asteroids or near-Earth asteroids themselves. So over 20,000 have so far been discovered. We're anticipating somewhere between 910 and 990 of diameter, at least 1 kilometer, and most of those have been discovered. They're hard to miss, so we think we found most of them. Somewhere between 10 and 30,000 of diameter, at least 140 meters, and we've discovered over 8,600 of those so far. At least these numbers are accurate as of like June 19 or something. We're expecting on the order of 10 million of diameter, at least 1 meter, and 300 to 500 million in total. And those are the sources there. I've got a bibliography at the end of these slides. All right. So here's what I want to say in response to that it can be misleading if all we're focusing on is bulk inventories. Because when we're talking about asteroids in particular, they're going to vary in their accessibility. Not all of them are equally easy to get to and contain attractive amounts of resources. So if we want a more honest and realistic appraisal of resources available, we need to factor for some practical restrictions on the exploitation of space resources. And in this talk, I want to focus on getting water from both near-Earth asteroids and the moon, because water is kind of a sine qua non when it comes to human exploration. We can't go anywhere without water. We can't really stay very long in places that don't have water. So that's a very much limiting factor when it comes to crewed missions, crewed settlement, and so on. So here's one important factor we have to be mindful of: energy budgets. How much fuel, how much energy does it take to get to a destination where there are resources and then to bring them back to wherever you want to use them? And just based on economics, your early NEA exploitation missions are always going to prioritize the most energetically accessible resources. And if it's going to take you more energy to get to an asteroid than it does to get to the moon, you're better off just going to the moon. So the first thing we're going to focus on would be asteroids that are at least as energetically accessible as the moon, that we could return back to cislunar space at or below lunar escape velocities, so less than or equal to 2.3 kilometers a second. And an estimate coming from some planetary scientists says that if you're looking at NEAs of at least 1 meter diameter, only 10 in power 14, so what is that, 100 trillion kilograms of material could be returned. That's total asteroidal material at that energy budget. Right, there Other estimates out there, okay, I'm not going to survey every single planetary science paper on the topic in this talk, but I will say that pretty much all of them that I've seen don't offer pictures dramatically different than what I'm going to describe here. And of course, if we're interested in water mining, we're probably interested in C-type asteroids. And Sanchez and McGinnis will tell us that we can expect those to be about 10% of the mass of the NEA population, and then those C-types are expected to be around 8% water by mass. So just do some simple calculations here, and we get that of this accessible NEA population, only 800 billion kilograms of water could be returned at that energy budget, and that would correspond to a sphere of water that would be a little over a kilometer in diameter. Notice that figure is 4 orders of magnitude less than the bulk inventory. All right, so we get a very different picture of what's available if we keep practical restrictions and limitations in mind. But, you know, energy budget isn't the only picture. We also care about orbital dynamics. All right, missions to asteroids have to be planned in very similar ways to missions to other planets. In fact, they're tougher because you can't rely on the atmosphere or the gravity to slow you down rendezvous. Okay, so you actually need to do all of your slowing down yourself if you want to match orbits with an asteroid. All right, so in terms of planning, in terms of timelines, all right, you're looking, you know, at planning these missions years in advance. They're likely to take years apiece. All right. Now, from a different paper that actually tried to estimate some of these timescales and windows of opportunity that focused on C-types of between 5 and 10 meters in diameter, if you add in the bigger objects, the numbers don't get much bigger because there's a lot fewer of them as they get bigger, all right? And they're looking at a return budget of 3 kilometers a second, so that's a more generous return budget than the Sanchez and McGinnis figure. They're thinking that somewhere around 1,000 C-type asteroids are accessible with an average of 5 windows of opportunity per month. Right. And what they're estimating, this is Jadik et al., they're estimating that your average water haul from that's going to be 70 tons per month. And that's if we realize all of the windows of opportunity that are open, which in practice would not occur. So how do you put that in perspective? Well, if you do a little math here, you'll find that that is an average rate of 0.42 gallons per minute. So go in the bathroom, turn on a faucet, that's 3 times as much water as you're getting per unit of time as we would get at the average rates here. And if that's our sort of supply from the asteroids, it would take us 5 months to fill a volume of water equal to the Saturn V's third stage tanks, 19 months to fill up the second stage tanks with waters, 29 months to fill up the first stage tank with water, and a full 3 years if you were trying to fill up a 2-meter deep Olympic-sized swimming pool, and most of them are deeper than 2 meters. Right. Hopefully we're getting a picture here that we can't rely on having a lot of any given resource if we're relying on near-Earth asteroids. So here's another way of sort of depicting that based on the Jadik et al. Figures. Here's your 6-foot-tall person next to the volume of water in a sphere form from 1 month a year and 10 years of haul. And I think the sphere on the left-hand side is about 25 meters in diameter. Don't remember the exact figures. So that's based on Jadik et al.'s sort of estimate of average return from those 5 to 10 meter C-types. So, all right, maybe asteroids aren't the best place to go to get water, right? There's not a whole lot that's easily accessible, and it's only going to come in this really slow, staggered trickle. So maybe the moon's a better bet if we're trying to get water from space. And of course, remember, water's not just for drinking, bathing, it's for growing crops, it's for radiation shielding, you can track it into propellant, right? There are all kinds of uses of water. And if you're trying to get water from the moon, the easiest way to do that would be to go to the permanently shadowed regions in the north and south poles, right? These crater basins that sunlight is permanently blocked by the crater rims. And of course, some of those crater rims are permanently illuminated. And so that's a great place to host some of your solar power stations because you've got permanent access to sunlight. Of course, those, that surface area of the permanently lit regions are only a few hundred square meters. So that's real prime real estate. We're going to have to figure out how to deal with that really quickly the moment someone gets up there. But anyway, permanently shadowed regions altogether total to about 31,000 square kilometers. And if the entirety of that surface area contains water ice at the concentrations measured by LCROSS in 2009, you're looking at slightly less than 3 trillion kilograms of water. Now, there's a lot of uncertainty in that figure. Is it more like an upper bound or more like a lower bound? We just don't know. You know, how deep do those deposits go? Are those deposits contained in every permanently shadowed region or only in a small percentage of them? All right, so it's within the realm of possibility that that number is much larger than what's actually the case. All right, could be much smaller than what's actually the case. We just don't know yet. All right? But if we want to think of that in a perspective that's a little more familiar, because I don't have a good understanding of what 1 trillion kilograms of water looks like, that would correspond to a sphere of a little less than 2 kilometers in diameter. And here's a sort of combined figure where we're seeing all the way on the right, you've got the Burj Khalifa for scale. It's about 830 meters tall, that building, next to a sphere of all of the water you would get from near-Earth asteroids based on the Sanchez and McGinnis figures. Then the next sphere over would be the water from the permanently shadowed regions, if they're all containing water ice at the concentration measured by L-Cross. And then next one after is the permanently shadowed region water plus the near-Earth asteroid water next to Humdrum Lake by comparison, New Melones Lake. All right. I'm hoping you're getting the impression that we are not talking about a terribly considerable quantity of a resource that we use for many, many, many purposes. So, I'm a philosopher, I'm an ethicist. I think about policy stuff related to space exploration. So I think there have to be implications for how we think about regulation of space mining on account of this. And yeah, advancements in space propulsion are definitely going to open up a greater share of near-Earth resources, right? If we've got greater energy budgets, there's just more and more we can get to. But, you know, the economics of the situation is always going to drive us to prioritizing the lowest cost things. And even if we have cheap laser propulsion, do you think it's going to be much cheaper than the alternatives? I mean, the people that own those laser propulsion systems are going to want to make as much money as they can out of it. So you don't think that's going to be priced to just barely outcompete alternative sources? So we're always going to be prioritizing the lowest cost choices. So we're always going to be trying to get to the easiest objects to get to from an energy perspective. And moreover, you know, we should just not plan policy around best case scenarios. So yeah, there might be some dramatic improvements in propulsion technology that make things easier to do, but if you're trying to form regulation and policy, that should not be what everything is planned around. All right, again, lowest energy objects are always going to be the most preferable from an economic perspective. So, I think it is not at all crazy to imagine that we exhaust all of the accessible water from near-Earth space. I didn't say all of the water, I said all of the accessible water, the stuff that's easy to get to. And it's even easier to imagine that we have used up everything that we've accessed at any given moment. Because again, think about that figure, about 5 windows of opportunity per month for C-type water mining, right? I mean, if you're only getting a little bit at a time, you're going to use that up before the next shipment arrives. So again, it's just completely misleading to focus on the bulk inventories. We need to focus and plan policies around what we're going to have at any given moment. And it seems like that's just not a lot of water. Right? So I think in no way do we have evidence supporting the idea that the use of space resources is going to free us from any need to think about sustainable resource practices. Right? Sustainability, you know, that dangerous S word for us, right? That needs to stay with us. Well, this is an interstellar conference, right? So I've got to connect this to interstellar travel in some way. Well, remember that prediction I made at the outset that we're not getting to the stars as human persons unless we at least get to the main belt asteroids in the first place. Well, I think this picture should call into question how likely it is that we get to the main belt asteroids in the first place. So look, if we don't use the stuff we get early on well, if we waste the water we get early on just sort of building opulent lunar hotels, putting it all into one area, if we don't use those resources to expand spaceflight capabilities, then it's going to call into question our ability to get out to the main belt asteroids to exploit their resources, to get out further into the solar system to exploit the resources from there. Right? So again, we can't take it as a given that this is going to happen. It won't happen unless we plan for it, unless we manage these things carefully enough to make sure that we can provision those kinds of missions. And if we don't do that, you know, if we don't plan on making sure we have the capacity to get to the main belt asteroids and further in the solar system, then crewed interstellar missions are just absolutely hopeless, right? And look, even if we get to the rest of the solar system, you got to worry about things like the way that human populations grow over time. I've got a couple friends that have a book chapter in a recent book where they're sort of arguing that, look, if humans continue to double in population at the historical rate, it's not going to take us too long to use up the entirety of the solar system, all right, to use up all of the available land area and the resources of it. And if we do that and we don't at the same time have set something aside to provision interstellar missions, those go away. Okay, so if you want to realize crewed interstellar travel, you've got to be an active proponent of it. You have to make sure that we all get together and agree to reserve some amount of our resources to devote to that end. Because, you know, I just don't have a lot of faith that the market is going to deliver this, right? It's going to take a concerted effort. It's going to take attention on our part to say, hey, yes, we need to prepare to realize this. It's not just going to happen without anybody trying to make it happen. So I think if you're interested in interstellar travel, you need to be interested in the careful regulation and use of space resources. So it not only matters, you know, who gets access to these resources, how the exploitation itself is regulated, but also how those resources are used. Because that's vital not only to ensure the expansion of human spaceflight capabilities, but really to ensure the mere possibility of many forms of interstellar travel. So here's my main takeaway. We should really just stop pretending and stop speaking and advocating for space as though it contains infinite, unlimited resources. I think that is a very inaccurate portrayal of the situations we're likely to find, and moreover, that sustainability is going to be an essential component to our thriving in space at all stages of the human expansion into space. So there's never going to be a point where we don't have to be concerned about sustainability, because we know, based on our history, we're bad about checking our growth. All right, we're bad about managing resources. Why do you think it's going to be any different in space? So unless we make a concerted effort to plan on having enough resources to do the things we want to do, you can't guarantee we'll actually be able to do those things. Thank you.
Noticed that when you were talking about utilizing near-Earth asteroid resources for water, you were using a delta V of, on the generous side, 3 kilometers per second. I submit that you've got to measure against the cost of bringing the water up from Earth, which is going to expand considerably the near-Earth asteroids that are exploitable at a lower delta V.
Well, yeah, so that's the question is, you know, how do the economics work in terms of what do you need to ensure profitability of the exploitation of C-types? And so in a different paper, Martin Elvis is going to say that your C-types have to be of a certain size and certain concentration of resources in order to make it profitable. So he's going to talk about, I think, a minimum 18-meter diameter needed to actually net a profit. And that they're on the order of 9,000 candidates at an outbound delta V of 4.5 kilometers a second. Elvis doesn't tell us about what sort of inbound delta V. And of course, that inbound figure is kind of the more important one, because you're probably bringing a lot more material back than you're taking out there to either, you know, attach something to the asteroid to bring it back, or to exploit in situ and then retrieve the resources. So the inbound figures tend to be the more important ones. And, you know, it turns out the numbers game, right? Okay, is it cheaper to get water down here? But of course, you know, fresh water here is kind of in short supply in many ways. So I imagine there's going to be a whole bunch of people on Earth that are going to make a big fuss if you're trying to take water off the planet and send it out into space.
We have desalination capacity.
Sorry?
Sure. Among other things, we can stop pretending we don't have desalination capacity. The world is mostly oceans. The idea we're running out of fresh water is risible.
Well, we have to
On top of that, can we stop pretending that planning anything makes it easier to save resources? We have an history of this. The greatest ecological disasters are in planned economies. This amounts to pretending that those doing the planning are more than human. They are not. And people will waste resources because they are not perfectly informed. No one is. I am not saying the market will allocate them magically. It won't. However, most regulations we write now will be short-sighted and not fully aware of the conditions when we get there. Another thing we can stop pretending is that we have exact population growth statistics. Because right now, the countries that are growing exponentially are those whose censuses we can't trust. And we have reason to believe the reality on the ground is completely different. So this humanity doubles every whatever? No, they're estimates. We don't know. First of all, we need accurate information before we do any of this planning.
All right, so there are a lot of things there, so let me try to remember each point here. So what was the first one? I think I've forgotten by now. Oh yeah. So
Desalination is impossible.
and that takes energy, and that energy has to come from somewhere. And again, it's an economic question. And yeah. I mean, I don't think the economics for bringing water to Earth from space are really matter. But so, yeah, I mean, we've got alternative ways of supplying new fresh water. The question is, how do you pay for it? How do you acquire the relevant energy to do so? And again, even if we have some of these, dramatically beneficial technologies when it comes to, cheaper energy production, there's still economic interest in driving up costs there. I mean, you're not going to build these systems if you're not going to make money off of them. As to the point about regulation, look, we're facing a very likely tragedy of the commons situation here. If all that happens is you have individual nations devising their own space policies and doing whatever the hell they want up there, they're going to use up whatever's been acquired at any given moment.
You are assuming all nations are going to abide by international treaties? We are dealing already with situations where you can make all the treaties you want to, at least half the world's going to ignore them. So clearly you need to come up with a solution that incentivizes good behavior, not international regulation. Because it's always up to the nation state. There are always going to be bad actors. And because we don't want to precipitate a world war, we do not check the bad actors.
So I don't think we're disagreeing on many points here. I mean, the response I want to give is, like, if you really want a crewed interstellar mission, we have to work together. We have to plan for that. It's not just going to come out of nowhere. The resources aren't going to be there unless we make sure that they're still there by the time we've got the technologies to do so. Does that take regulation? Is it nations? Is it individual actors or corporations? I don't really care. What I care about is how do we think about the use of these, in many respects, limited resources. And to ignore the question, to say that it's hopeless because we haven't solved these problems here, I think really dooms the future of crewed interstellar travel.
Well, let's take that discussion to a coffee break, but we have another question here.
I'm minded of a quote that happens to be on a building where I live, that the current boom in petroleum production is clearly unsustainable. Within 5 to 8 years, we're not going to have it anymore. That quote was from a U.S. Geological Survey in 1890. If you study anything about the economics of resource production, this is not mysterious. This is well known in economics. The original work was done on forestry in the 18th century. Nothing that you said about the economics of resource production is in any way unique to space. Every single natural resource of any kind, at any moment, yes, people exploit that which is economically easiest to get with the technology of the day at the price then prevailing. And every natural resource ever known in the history of mankind, as soon as those resources are not as easy to get, we have this mechanism called price. The price starts to go up. Suddenly that changes what is economically exploitable, what is worth going after. The known reserves change and expand. It is, if you're worried about a tragedy of the commons, use some freaking ownership and take it out of the commons. Give it to people who pay some attention to selling to the highest price value asset. We can fix that.
But I mean, the question isn't merely about ownership. It isn't about who's engaging in activities. It's about what activities they're engaging in. All right. So I'm not talking just about access. I'm not talking about who are the people that are actually winning and losing here. I'm talking about if the resources are scarce in the way that the data here suggests they are, there's only so much you can actually do with that. And again, if you think that crewed interstellar travel is a goal we ought to realize, that's a use of space resources that has to be sort of supported throughout. It's not just going to magically be the thing that's the best way to spend the money on those resources. So, you know, again, I want to shy away from thinking that the economic picture here is going to give us the total picture, and it's going to deliver the use of the resources that actually is the most ethically defensible use of those resources. And I'll defend that position about economic activity here. We waste a lot. You know, wasting things makes money, and that's what's stupid. That's what has to change. All right, and we're going to hear from other people at various points about this model we have of this very consumer, free market-driven thing. I mean, don't expect that to deliver your favorite projects.
Jim, I thought that was a very interesting talk. One thing I did want to point out, you raised the issue of this idea of this ever-expanding population, but that's not what demographers actually think is going to happen. What's likely to happen is we're going to get to be around between 9 and 12 billion people level off, and our population is going to begin to decline. And we're already seeing that in East Asia and other parts of the world. You know, for example, in Japan, the population right now is 125 million. By the end of this century, the projections are it'll be about 45 million. And the association is that when education levels go up, fertility seems to go down. It's called a fertility transition. So I think one has to be very careful about connecting just exponential population growth to this problem. I agree with the basic point you're making, but population is very complex because it's tied into other things like education.
Yeah, and so that's sort of drawn from, again, that was the Milligan-Elvis paper, where they're not just talking about humans on Earth. It's talking about, you know, suppose we've got space settlements, suppose we're starting to colonize all sorts of other planets. What's going to happen there? How easy is it going to be for the sort of growth of humanity to outpace the resources of the solar system? And so, you know, that's a point sort of borrowed from those two. So I can maybe try to see what they might have to say in response to a question like that.
Yeah. Your model of the near-Earth objects really basically looked as if there was a wall at accessibility somewhere around 2.5 to 3. But there is no wall. It's a fuzzy wall.
Right, right.
The accessibility gets increasingly hard, and therefore at a constant price per delta V, the price goes up as you go further out. But the other consequence of accessing water from near-Earth space is that the cost of delta V goes down because you're spending money to buy delta V, and that gives you more delta V to accumulate more delta V. So when you look at the resources of the solar system, what you end up doing is saying that as your space industrialization expands, you have access to larger and larger portions of the solar system. So at the beginning, you may access the low delta V near-Earth objects, but using that delta V, you can access all of the near-Earth objects, which allows you to access the main belt objects, which allows you to access the Kuiper belt objects, which allows you to access the Oort cloud objects.
There's an if
If
there.
we're going to the stars, we will be going to the Oort cloud first.
Yeah.
And there are 1 trillion objects in the Oort cloud.
Yeah.
It's possible we will exhaust those sometime, but not within any foreseeable future.
But there's an if there that I don't think came out as much as it should have. And I agree, yes. I mean, if we've got a bigger energy budget, we can get to more. And if we use what we get to go further, yes, we can go further and get more resources. But if we don't use early spoils to increase capacities, if all we do is build hotels on the moon and fill them with you know, pools for really rich people to swim in, and that's the only way that that resource gets used, you're not creating the propellant that lets you go further afield, right? So the whole point here is that if you want to go farther than the things that are easier to get to the moon, you have to make sure you're using some of what you get to go further. And what I'm saying is that it's not a foregone conclusion that that's actually going to happen. That does take effort. That takes planning to make sure that those things are used in that way. And maybe the market's going to deliver it, maybe it won't.
Let's end here and thank our speaker again.